The universe is not a random scattering of stars. It is structured as an immense cosmic web, a vast architecture of glowing filaments and dark, empty voids. This is the largest structure we know, and it holds 50 profound mysteries about the very nature of reality. By the end of this journey, you will understand the hidden forces that built the cosmos and the fundamental puzzles that still confound our greatest scientists. We will confront the invisible grip of dark matter and ask why entire galaxies spin in eerie synchrony. What single cosmic mystery keeps you awake at night, wondering about the fabric of it all? The first and perhaps greatest mystery is the origin of the filaments themselves. These are not merely threads in space. They are the fundamental backbone of all cosmic structure, the colossal scaffolding upon which every galaxy and cluster is hung. Their existence forces us to ask a profound question. How did a universe that began in a state of near-perfect smoothness, a hot and dense soup of particles, ever become so lumpy, so structured on such an unimaginable scale? The answer appears to lie in the faintest of whispers from the dawn of time. Scientists believe that tiny quantum fluctuations, random microscopic ripples in the fabric of reality, were present in the first fleeting moments after the Big Bang. During a period of hyper-expansion known as inflation, these subatomic imperfections were stretched to sizes beyond human comprehension. They became the seeds, the cosmic blueprint for all the structure we see today. Where a region was ever so slightly denser, its gravitational pull was a tiny bit stronger. Over billions of years, this gravity acted like a cosmic amplifier, drawing in more and more dark matter and gas. The densest spots collapsed into the great nodes where galaxy clusters now reside. The material between them, pulled by the competing tugs of these growing nodes, was stretched into the long, thin bridges we call filaments. It is a story written by gravity, but it began with a quantum whisper. This cosmic blueprint, however, was drawn by an invisible hand. We call this mysterious architect dark matter, and its true nature is the second great mystery of the cosmic web. We cannot see it, touch it, or directly measure it with any instrument we have ever built. Yet we know it is there because of its immense gravitational pull. Think of a merry-go-round spinning in a dark park. You cannot see the children pushing it, but you can see the structure whirling faster and faster, a clear sign of an unseen force at work. Dark matter is the unseen child pushing the entire universe. Its gravity provides the essential scaffolding, the hidden skeleton, upon which the luminous filaments of galaxies are draped. Without this dark framework, the cosmic web would simply not exist. The ordinary matter that makes up stars, planets, and us simply did not have enough gravitational muscle on its own to pull the universe into such a vast and intricate structure in the time available since the Big Bang. So what could this invisible substance be? The leading idea is that it is a new, exotic type of particle, one that rarely, if ever, interacts with normal matter except through gravity. Scientists at facilities like the Large Hadron Collider are smashing particles together at nearly the speed of light, hoping to create one of these elusive dark matter particles in the debris. Other experiments are buried deep underground in old mines, shielded from cosmic rays, waiting with ultra-sensitive detectors for the faintest tick of a dark particle passing through. For now, it remains a ghost in the cosmic machine, the most dominant material in the universe and yet its greatest secret. But if dark matter is the cosmic skeleton, what about the flesh and blood? We have a third profound mystery, one that concerns the very stuff we are made of. All the atoms that form stars, planets, and life itself are known to scientists as baryonic matter. Our most trusted models of the Big Bang predict precisely how much of this ordinary matter should exist in the universe today. Yet when we add up everything we can see, from the brightest galaxies to the faintest gas clouds, we find nearly half of it is simply missing. It is a galactic scale case of lost luggage, and the prime suspect for its hiding place is the cosmic web itself. The filaments are not just empty highways. They are thought to be filled with an incredibly diffuse, superheated gas, a tenuous fog known as the warm-hot intergalactic medium, or WHIM. This is not gas you could see with a telescope. It is so hot that it glows not in visible light, but in far more energetic X-rays, and it is so thin that a single coffee mug full of it would contain only a handful of atoms. Finding this WHIM is like trying to spot a wisp of steam in a darkened cathedral using only a faint flashlight. So how do we hunt for something so elusive? Astronomers use a clever trick. When the light from a brilliant, distant object like a quasar travels for billions of years to reach us, it passes right through these cosmic filaments. The specific gases in the WHIM absorb very particular colors or wavelengths of that brilliant light, leaving behind a unique fingerprint, a series of dark lines in the quasar spectrum. It is the cosmic equivalent of finding a specific set of fingerprints at a crime scene. These absorption lines are the telltale sign that the missing baryons are there, woven into the vast, hot tapestry of the web. Solving this mystery is crucial because it tells us the final whereabouts of the ordinary matter that builds everything we know. It completes the inventory of our cosmic home. Yet for all its grandeur, this cosmic architecture would be a dark and empty stage without its brightest performers. How did the first stars and galaxies, the very first lights in a black and silent universe, ignite within this cold, dark scaffolding? This is the fourth great mystery, a question that takes us back to a time so ancient it defies comprehension. The universe was a simple, shadowy place, filled only with dark matter and a smooth, dull fog of hydrogen and helium gas. There were no stars, no galaxies, and no sources of light. For hundreds of millions of years, the cosmos was locked in a profound darkness known as the cosmic dark ages. The key to ending this eternal night was the invisible hand of dark matter. Its gravity had already begun to weave the first faint threads of the web, creating dense knots within the filaments called dark matter halos. These halos were not made of stars but of pure, invisible matter, and they acted as gravitational traps. Vast clouds of that primordial gas, drawn in by the halo's irresistible pull, would sink to the center, becoming so incredibly dense and hot that nuclear fusion finally sparked. The very first star was born. We call these pioneering suns' population 3 stars, and they were unlike anything that exists today. They were behemoths, hundreds of times more massive than our own sun, burning ferociously bright and dying young in colossal supernova explosions. But observing this dawn of creation is one of astronomy's greatest challenges. The light from these first stars and tiny, infant galaxies has been traveling for over 13 billion years to reach us. The expansion of the universe has stretched their once brilliant visible light into the faint, long wavelengths of infrared radiation. It is like trying to hear a whisper from across a roaring stadium. Our most powerful telescopes, like the James Webb Space Telescope, are essentially giant heat sensors designed specifically to pick up these ancient infrared whispers. They are our time machines peering back to see the faint, red smudges of these first gatherings of stars, nestled securely within their dark matter cradles. Each new observation brings us closer to understanding the moment the cosmic web first began to glow, transforming a structure of shadow into a universe of light. But these first galaxies were not just passive lights, they were spinning, and the way they spin holds a fifth profound mystery. Across vast stretches of the cosmos, astronomers have observed something that should not happen by random chance. The rotation axes of galaxies, the imaginary line around which a galaxy spins, show a startling tendency to align with the cosmic filaments they call home. A galaxy living within a long filament will often spin in a way that its axis points along the filament's length, as if it were a bead on a wire twirling around that wire. Other times, its spin will be perpendicular, like a rolling wheel within the cosmic tunnel. This is not a local quirk. It is a large-scale, coherent pattern, a synchronized dance of angular momentum that spans hundreds of millions of light years. How can galaxies so far apart, with no possible communication between them, agree on which way to turn? The leading explanation takes us back to the very beginning of everything, to a concept known as tidal torque theory. In the infant universe, the primordial clouds of dark matter and gas that would one day become galaxies were not perfectly smooth. They had slight, irregular shapes like lopsided potatoes. As these protogalactic clouds fell into the gravitational wells of the emerging cosmic web, they experienced a differential pull, a tidal force. Think of holding a cucumber by one end. The end you are holding feels a stronger pull of gravity than the far end. This difference in force creates a torque which makes the object start to spin. In the cosmic context, the far stronger gravitational pull from a massive filament or a nearby dark matter node would tug on one side of a gas cloud more than the other. This tidal torque is what is thought to have given most galaxies their initial spin. But this alone does not explain the eerie alignments we see today. For that, the initial conditions must have been just right, with the shapes and orientations of those first clouds imprinted by the specific geometry of the filament they were born in. It suggests that the cosmic web did not just dictate where galaxies would form, but also how they would move, setting their spin in motion billions of years ago. This large-scale coherence is a fossil record of the universe's earliest gravitational forces, a ghostly hand that still guides the celestial dance. Could there be other, more exotic forces at work, shaping the angular momentum of the cosmos on the grandest of scales? The mystery of galactic spin forces us to look ever deeper into the hidden architecture of reality itself. Between the brilliant threads of the cosmic web lie the true titans of emptiness. These are the cosmic voids, immense regions of space so profoundly empty they challenge our very understanding of a populated universe. While the filaments and nodes are the bustling cities and highways of the cosmos, the voids are the continent-sized deserts, spanning hundreds of millions of light years with almost nothing inside. The sixth great mystery asks why these voids exist at all, and what their stark emptiness can teach us about the forces that shaped everything. According to our models, the voids are not completely empty. They are the inverse of the dense filaments, the low-pressure zones in the primordial sound wave of the Big Bang. As gravity pulled matter into the filaments and clusters, it simultaneously evacuated these vast territories, leaving behind only the most tenuous traces of gas and a few rare, isolated galaxies. But the boundaries of these voids are not sharp walls. They are more like gentle slopes where the density of matter gradually increases from nothing to the rich environment of the filament. It is the difference between the deep ocean floor and the shoreline, a slow, steady rise into a world of structure. The real puzzle begins with the galaxies that do, against all odds, form within these cosmic deserts. How does a galaxy come to be in a place with so little raw material? These isolated systems, often called void galaxies, are some of the most unusual in the universe. Without the constant gravitational harassment and mergers that shape galaxies in crowded clusters, void galaxies are often like quiet, solitary islands. They tend to be smaller, slower to evolve, and can retain a more primitive, pristine state, as if time itself moves more slowly in the void. Some even appear to be bluer and more actively forming stars than their counterparts, perhaps because they have not yet exhausted their limited supply of cold gas. Their very existence forces us to refine our models of galaxy formation. It suggests that even in the deepest emptiness, the subtle whispers of dark matter's gravity can still, on rare occasions, gather just enough material to spark a single, lonely star city. These solitary galaxies are natural laboratories, showing us what a universe without neighbors looks like, and challenging us to understand how the cosmic web's grand design creates both immense emptiness and isolated islands of life. This intricate cosmic architecture, with its bustling filaments and silent voids, leads us directly to a foundational crisis in cosmology. For centuries, a simple but powerful idea has guided our understanding of the universe, the cosmological principle. It states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the cosmos should look the same from every location, like a perfectly mixed batter where any spoonful is identical to the next. Isotropic means it should look the same in every direction you gaze, with no special center or preferred axis. This principle is the bedrock upon which Einstein's theory of relativity and our entire model of the Big Bang is built. It allows us to extrapolate from our tiny corner of the cosmos to the universe as a whole. But the cosmic web presents a stark challenge. It is the very opposite of a smooth, featureless soup. It is a universe of stark contrasts, of dense cities and empty deserts, a place with clear structure and direction. So, does the existence of the cosmic web shatter this foundational principle? The answer is a delicate and profound no, but with immense consequences. The salvation of the cosmological principle lies in the scale of the observation. When we zoom out far enough, when we smooth over the universe, not by millions of light years, but by billions, the distinctions begin to blur. Think of the view from an airplane window. As you climb higher, the specific details of individual cities, roads, and farms merge into a single, textured landscape. You can no longer pick out a single house or a single street. From this ultimate vantage point, the great walls and vast voids of the cosmic web average out. If you were to take a cube of space 1 billion light years on a side, its overall density of matter would be roughly the same as any other billion light year cube anywhere in the universe. The principle holds, but only on the grandest possible stage. This resolution, however, raises a deeper question. What is the true, fundamental texture of reality? Is it the smooth, average universe of our equations, or is it the vibrant, structured web of filaments and voids that we actually observe? The cosmic web does not violate the cosmological principle, but it forces us to define its limits, to acknowledge that our most fundamental assumptions about the cosmos are only valid when we ignore its most striking and beautiful features. This tension lies at the very heart of modern cosmology, a reminder that the universe is far more complex and wondrous than any simple principle can fully contain. Deep within the cosmic filaments, an invisible force weaves through the darkness. We have detected the ghostly presence of magnetic fields, threading the vast gaseous highways of the web. This is the eighth great mystery, a puzzle that asks how these fields came to be and what hidden role they play in the story of cosmic structure. We are familiar with magnetic fields from our own planet, a protective shield generated by the churning of molten metal in its core. But the cosmic filaments are a different reality altogether. They are composed of a plasma, a superheated, electrically charged gas so incredibly diffuse that atoms rarely ever collide. How could a magnetic field be generated and sustained in such a near-perfect vacuum? The origins are thought to be ancient and incredibly subtle. One leading theory suggests that in the earliest moments of the universe, even before the first stars, minuscule magnetic seeds were created by the turbulent motions of that primordial plasma. As the cosmic web formed, these weak, primordial fields were stretched and amplified by the immense flows of gas sliding along the filaments, much like taffy being pulled into long, thin strands. Another possibility points to the violence of the first galaxies and quasars, whose powerful jets and stellar winds could have blown magnetized material out into the intergalactic medium, seeding the filaments with their magnetic imprint. Once established, these fields, though incredibly weak millions of times fainter than Earth's own magnetic field, exert a quiet but profound influence. They can guide the movement of charged particles, affect how heat travels through the gas, and even influence the collapse of giant gas clouds to form new stars and galaxies. They are the cosmic web's silent conductors, orchestrating processes we are only beginning to perceive. Unraveling this mystery requires us to look for the faintest signals, the subtle polarization of light, or the specific signatures in radio waves that betray the field's presence. It is a reminder that the universe is not shaped by gravity alone, but by a symphony of forces, some of which we are still learning to hear. The silent magnetic fields woven through the cosmic web are themselves subject to a far greater and more relentless force, one that dictates the ultimate destiny of all structure. This brings us to the ninth and perhaps most profound mystery, the ultimate fate of the cosmic web itself. We live in a universe not merely expanding, but accelerating in its expansion, driven by the enigmatic repulsion of dark energy. This force acts as cosmic antigravity, and its long-term influence on the grand architecture we have explored is both chilling and inevitable. For billions of years, gravity has been the master builder, patiently assembling the filaments, nodes, and clusters. But dark energy is the great unraveler, working on a timescale so vast it dwarfs the current age of the universe. In the near-cosmic future, measured in tens of billions of years, the consequences will begin to unfold. As the space between filaments stretches at an ever-increasing rate, the flow of fresh gas that fuels the birth of new galaxies will be severed. The cosmic web will begin to starve. Galaxy clusters, those bustling metropolises, will become isolated islands, their local groups of galaxies bound together by gravity but cut off from the rest of the universe. The vibrant cosmic ecosystem will slowly shut down, but this is only the beginning. The most extreme prediction is a scenario known as the Big Rip. If the strength of dark energy increases over time, its repulsive force could eventually overcome every force that holds things together. It would first tear apart the cosmic web, severing the gravitational bonds between galaxy clusters. Then it would rip apart individual galaxies. As the acceleration becomes infinite, it would tear apart stars from their galaxies, planets from their stars, and finally, even atoms and atomic nuclei themselves. The universe would end in a final, silent flash of disassociated fundamental particles, forever isolated from one another in an ever-widening emptiness. A less violent but equally bleak future is the heat death. Here, dark energy continues its acceleration but does not intensify to rip everything apart. Instead, the universe simply expands forever, becoming colder and darker. The cosmic web, having long since been pulled apart, becomes a relic. The last stars burn out, and black holes slowly evaporate over unimaginable eons. What remains is a near-perfect vacuum, a cold, dark, and utterly lonely cosmos where the grand architecture of filaments and voids is nothing but a fossilized memory in a long-dead universe. This cosmic fate forces us to confront a humbling truth. The magnificent web we see today, with its brilliant galaxies and vast magnetic highways, is a temporary structure, a fleeting moment of cosmic glory in a narrative that ultimately trends toward silence and isolation. The mystery is not just what will happen, but what this inevitable end tells us about the fundamental nature of the dark energy that seems to hold the final word. The faint glow of the cosmic microwave background is the oldest light in the universe, a snapshot of the cosmos when it was a mere infant. This afterglow is not perfectly smooth. It is mottled with tiny variations in temperature, hot and cold spots that are the direct imprint of those primordial quantum seeds. These minute fluctuations are the cosmic blueprint, the genetic code from which the entire vast web of filaments and voids would eventually grow. A slightly denser patch in this ancient radiation corresponds to the seed of a future supercluster, a slightly cooler patch to the cradle of a future void. For decades, our most precise satellite maps of this background radiation have beautifully confirmed this story, its statistical patterns matching our predictions almost perfectly. Almost because scattered across this baby picture of the universe are a handful of strange, persistent anomalies that refuse to fit the narrative. The most famous of these is the cold spot, a vast, unusually cold region in the southern sky that is far larger and far colder than our models say it should be. It is a cosmic bruise that defies easy explanation. One tantalizing, if speculative, theory proposes that this cold spot is not a flaw in the data but a shadow. It could be the imprint of an immense cosmic void, a truly gargantuan emptiness lying between us and the background radiation. As light from the cosmic microwave background travels through such a void, it must climb out of a gravitational well, losing energy and stretching to longer, cooler wavelengths in a process known as the integrated Sachs-Wolf effect. This would make that region of the sky appear anomalously cold. If true, it would mean the cold spot is a window into a void of staggering scale, a desert so vast it challenges our understanding of how the cosmic web formed. Other, more exotic explanations have been proposed, including the collision of our universe with another bubble universe in the multiverse. While this remains highly speculative, these anomalies force us to question the very initial conditions of everything. Was the early universe not as simple and uniform as we thought? Do these cosmic wrinkles hint at a physics that predates the Big Bang itself? The silent, frozen light of the cosmic microwave background holds the secrets to the web's birth, and its faintest imperfections may be the most important clues we have. These precise maps of the cosmic web are now forcing us to confront a glaring inconsistency in our most fundamental cosmic measurement. The Hubble constant, the number that describes how fast the universe is expanding today, is at the heart of a modern crisis known as the Hubble tension. Simply put, different methods of measuring this expansion rate are giving us different answers, and the cosmic web itself is becoming a key witness in this trial. One way to measure the Hubble constant is to look at the early universe at the cosmic microwave background. This gives us a very precise foundational value. Another way is to measure distances and speeds of nearby stars and galaxies, a cosmic distance ladder built from Cepheid, variable stars and supernova. The problem is that the local, late universe measurements consistently suggest an expansion rate that is faster, by a significant margin, than the early universe prediction. It is as if the universe started expanding at one speed, but has since decided to accelerate beyond what our models allow. This is where the cosmic web offers a third, completely independent path. By mapping the three-dimensional distribution of millions of galaxies, scientists can measure something called baryon acoustic oscillations. These are the fossilized imprints of sound waves that traveled through the primordial plasma before the atoms formed. These waves set a preferred scale, a standard ruler, in the early universe. We know exactly how long this ruler should be. By observing how this standard ruler appears stretched or compressed in our maps of the cosmic web, we can measure cosmic distances with incredible precision, and from that calculate the Hubble constant. The results are deeply intriguing. They often land somewhere in the middle of the other two methods, not fully agreeing with either. This independent check from the large-scale structure tells us that the tension is real and not simply an error in one single measurement technique. The cosmic web is not just a beautiful structure, it is a precision instrument, and its measurements are deepening the mystery rather than solving it. This discrepancy suggests that our standard model of cosmology, for all its success, might be missing a crucial ingredient. Perhaps dark energy is not constant but evolving. Maybe dark matter has properties we have not yet imagined, or there could be entirely new physics operating on the largest scales. The Hubble tension, revealed by the structure of the cosmic web, is a clear sign that our understanding of the cosmos is incomplete, pointing toward a discovery that could reshape our entire cosmic story. The universe orchestrates alignments on a scale that defies belief. Deep within the filaments of the cosmic web, astronomers have uncovered a phenomenon so strange it seems to whisper of a hidden order. The most powerful engines in the cosmos, quasars, are not pointing randomly into the void. A quasar is the intensely bright nucleus of a distant galaxy, powered by a supermassive black hole feasting on surrounding matter. This accretion process often creates twin jets of radiation and particles that blast out into space along the black hole's rotation axis, like a lighthouse beam defining its spin. When scientists mapped the positions of thousands of these cosmic lighthouses, they found their beams were not shining in every possible direction. Instead, the rotation axes of these quasars, separated by billions of light years, showed a startling tendency to align with each other, pointing in similar directions across the vast expanse. This is not a local effect. The alignment appears to be correlated with the large-scale structure itself. The spin axes of these monstrous black holes seem to be lining up along the same cosmic filaments that host their galaxies. How can objects so far apart, with no possible communication between them, coordinate their spin? The only conceivable force capable of such a grand-scale coordination is gravity, as mediated by the cosmic web. The leading theory suggests that the same tidal forces that set galaxies spinning also imprinted a preferred direction on the gargantuan gas clouds that collapsed to form these supermassive black holes. As these primordial clouds, weighing millions of suns, slid into the gravitational trough of a filament, they would have experienced a subtle but consistent torque. This universal nudge, applied billions of years ago across the entire structure, may have set the initial spin for everything that formed within that filament, from the galaxies right down to the black holes at their hearts. The quasars, with their brilliant directional jets, are simply the most visible signposts of this ancient universal spin. This alignment is a ghostly fossil, a memory of the universe's first gravitational influences preserved in the spin of its most violent objects. It implies that the cosmic web does not just tell matter where to go, but also how to move, dictating the dance of reality from the largest filaments down to the whirl of space-time around a black hole's abyss. The silent alignment of quasars hints at a cosmic web that does more than just arrange matter. It also delivers the fuel for creation itself. This brings us to the vital mystery of how galaxies grow, a process centered on the very nature of the gas within the filaments. Galaxies are not closed systems. They are dynamic engines that require a constant supply of fresh, cold gas to form new stars. Without this fuel, a galaxy would burn through its reserves in a cosmic blink, its star formation sputtering out. The ultimate source of this gas is the cosmic web, the vast reservoir of primordial material from which all structure formed. But how does this raw material, scattered across millions of light years, actually make its way into a galaxy's heart? The answer lies in two competing modes of cosmic delivery, a hot and a cold river flowing into the galactic reservoir. For the most massive galaxies, those sitting at the crowded nodes of the web, the journey is a violent one. As gas falls into the deep gravitational well of a galaxy cluster, it is compressed and heated to extreme temperatures, millions of degrees, until it glows in X-rays. This superheated gas is a reluctant fuel. It is too energetic to collapse easily and form stars. For star formation to occur, this hot gas must first cool down, a slow and inefficient process that often fails to deliver enough fuel, leaving many giant galaxies red and dead, their star formation quenched. But for smaller galaxies like our own Milky Way, a more direct and efficient highway exists, the mysterious process of cold flow accretion. Imagine a mountain stream flowing down a rocky slope, reaching a lake without ever evaporating. In a similar way, computer simulations reveal that dense streams of cold gas can travel along the cosmic filaments, flowing directly into a galaxy without being heated to extreme temperatures. These rivers of cold gas are protected within the dark matter filaments, shielded from the harsh intergalactic environment. They provide a rapid, high-capacity fuel line, allowing galaxies to form stars at a prodigious rate. This cold gas does not simply pour in untouched, however. As it penetrates the galaxy's halo, it can be shock-heated, or it might mix with the galaxy's own hotter gas. The final journey inward from the outer disk to the star-forming nurseries is a complex ballet of cooling, condensation, and collapse. Observing this process directly is a monumental challenge, as the cold flows themselves are dark and difficult to detect. Astronomers hunt for the faint signatures of this gas, using the light from distant quasars to illuminate the streams, or looking for the telltale glow of hydrogen in specific wavelengths. The balance between the hot and cold modes of accretion dictates the life and death of a galaxy, shaping its growth from a tiny spark in the dark to a brilliant spiral of billions of stars. The cosmic web is not a static scaffold, but a dynamic circulatory system, and the mystery of how its gaseous blood flows is the mystery of how galaxies are born, live, and ultimately fade. This coordinated galactic drift points toward a horizon we cannot see, hinting at a 14th mystery known as the dark flow. Astronomers have mapped the motions of thousands of galaxy clusters, and they have found something deeply unsettling. These immense structures, each containing thousands of galaxies, are not just moving apart with the general expansion of the universe. They also share a subtle, additional velocity, a bulk flow, as if they are all being tugged in the same specific direction. This is not a random drift. It is a coherent, collective motion on a scale of billions of light years, a current in the cosmic ocean that should not exist. According to our standard model, the gravitational pull from all the visible matter in the observable universe should be the only force guiding these large-scale motions. The distribution of galaxies and dark matter in the cosmic web should create a gravitational landscape that explains every push and pull. Yet the dark flow persists, a current that points towards something massive lying far beyond the edge of everything we can see. What could possibly exert such a gravitational pull? One extraordinary possibility is that the flow is evidence of a cosmic structure so immense it defies our current understanding, a concentration of mass that lies outside our observable bubble. Because the universe is only 13.8 billion years old, we can only see the light that has had time to reach us. There is a fundamental horizon to our perception. The dark flow suggests that the cosmic web we map is just a small neighborhood in a much larger metropolis, and the gravity from a distant, unseen supercluster, perhaps a gargantuan knot of matter in the greater universe, is reaching across the void and pulling everything in its direction. Another, even more speculative idea is that the flow is a remnant scar from the violent process of inflation, a time when the universe expanded faster than light. The physics of that primordial epoch could have imprinted a preferred direction on the very fabric of space-time, a directional bias that still guides motions today. For now, the dark flow remains a controversial and hotly debated topic. Some analyses claim it is a statistical fluke, while others insist the signal is real. Its potential confirmation would be one of the most profound discoveries in cosmology, forcing us to redraw our maps of reality and accept that the true architecture of the cosmos extends into realms we may never directly observe. This predicted plumpness of the cosmic web's threads stands in stark contrast to what some telescopes are now revealing. Our most sophisticated computer simulations of the universe, which model the gravitational pull of dark matter and the complex behavior of cosmic gas, often paint the filaments as rather thick and diffuse structures. Yet when astronomers manage to glimpse these cosmic highways directly, they sometimes appear surprisingly slender and well-defined, like sharp, dark rivers against a brighter background. This discrepancy is the 15th mystery, a puzzle that forces us to question whether we truly understand the turbulent life cycle of the gas that flows through the universe. The simulations are not wrong, but they may be missing a key piece of physics. In the virtual cosmos, gas falls into the filaments and is heated by the shock of collapse, puffing it up into a thick, hot haze. But in reality, this gas must somehow be cooling down and condensing much more efficiently than we thought possible. How does it lose its heat so effectively? One answer may lie in the heavy elements forged inside stars. When the first generations of massive stars exploded as supernova, they seeded the primordial hydrogen and helium with atoms like carbon, oxygen, and iron. These metals, as astronomers call them, are far more efficient at radiating away heat than simple hydrogen. This enriched gas flowing into the filaments can cool faster and collapse into denser, colder, and therefore much thinner streams. But there is another, more violent force at work, one that might paradoxically make the filaments thinner by making them hotter. This is the phenomenon of feedback. When a supernova explodes, or when a supermassive black hole at a galaxy's core goes through a ferocious feeding frenzy, they unleash titanic winds and jets of energy. This feedback can blast gas out of a galaxy, but it can also heat the surrounding filament from the inside, preventing the diffuse outer layers of the gas from cooling and falling in. The result is like a gardener pruning a bush, shearing away the fuzzier, outer parts of the filament and leaving behind a denser, more defined central core. The gas that remains in this trimmed filament is then better at cooling and flowing efficiently along the cosmic highway. Even the nature of dark matter itself could be playing a role. What if dark matter is not completely cold and collisionless? What if these particles can interact with each other through some unknown force, creating a kind of friction? This self-interacting dark matter would also tend to form tighter, more concentrated filaments, smoothing out the fluffy halos and leading to a sharper cosmic web. The unexpected thinness of these universal threads is more than a minor detail. It is a direct clue telling us that the cosmos is not a placid place. It is a dynamic system where the violent lives and deaths of stars and the ferocious appetites of black holes reach out and sculpt the largest structures in existence, all the way down to the sharpness of a single glowing filament in the dark. That sharp, thin filament of gas was the very highway for the universe's first dawn. The end of the cosmic dark ages was not a gentle sunrise, but a violent revolution that changed the fundamental nature of the cosmos, and the cosmic web was its essential delivery system. This is the 16th mystery, the epoch of reionization. For hundreds of millions of years, the universe was a neutral fog. The hydrogen gas filling all of space had its single electron bound to its proton, making it opaque to certain kinds of light. The first stars and galaxies that flickered on within the web's filaments were at first imprisoned, their brilliant ultraviolet light immediately absorbed by the surrounding hydrogen fog, unable to travel far. But these first stars were behemoths, and they emitted so much energetic radiation that they began to rip the electrons away from the hydrogen atoms in their immediate vicinity, creating growing bubbles of ionized transparent plasma. The question is, how do these isolated bubbles merge to create a universe that is completely transparent to light today? The cosmic web provided the answer. The filaments acted as pre-cleared pathways, channels of slightly denser gas that connected these early stellar nurseries. Radiation from the first stars and quasars did not have to blast its way through a uniform wall of fog. Instead, it could travel much more efficiently along these cosmic fiber optic cables, reaching distant regions and igniting new ionization fronts far from its source. The structure of the web guided the light, allowing the bubbles to grow and connect along the filaments long before they could merge in the empty voids. This transformed the universe from a collection of isolated clearings into a fully ionized cosmos in less than 1 billion years. Without the web's architecture, this global transformation might have taken far longer or perhaps never been completed at all. The filaments were not just the scaffolding for the first galaxies, they were the conduits for the light that set the entire universe free. Deep within the cosmic voids, where most galaxies are lonely and small, astronomers have stumbled upon a true paradox. Drifting in the emptiness are colossal ghost ships, galaxies as large as the Milky Way but so faint they were nearly invisible to our telescopes. These are the ultra-diffuse galaxies, and their existence in the barren voids is the 17th profound mystery. A galaxy this size should be packed with hundreds of billions of stars, a brilliant pinwheel of light. But an ultra-diffuse galaxy contains only 1% of the stars of a normal galaxy. Its light smeared across an immense volume, creating a spectral haze against the dark. Finding such a large, faint object in the emptiest places in the universe is like discovering a vast, empty city in the middle of a desert. A metropolis built for millions but inhabited by only a handful of people. How did these ghostly giants form, and how do they survive in an environment with so little raw material? The answer seems to lie in a unique and quiet life history dictated by their isolated address. In the crowded filaments and clusters, galaxies grow through violent mergers and by feasting on smaller neighbors, a process that efficiently funnels gas into their cores to create dense, star-filled disks. But in the deep void, such cosmic drama is absent. An ultra-diffuse galaxy may have formed from a vast cloud of gas that collapsed very slowly over billions of years in an environment so quiet and uneventful that the gas was never compressed enough to trigger vigorous star formation. Its star-making machinery simply sputtered, creating a few stars here and there, leaving the galaxy a vast, dark, and mostly empty expanse. Their survival, however, points to an even deeper secret. A galaxy this large and spread out should be incredibly fragile, easily torn apart by the gravitational tides of even a passing dwarf galaxy. The fact that they remain intact suggests they are held together by an immense amount of dark matter. These ghostly giants may be among the most dark matter-dominated objects in the universe, their invisible halos acting as massive protective cocoons that shield their delicate stellar populations from harm. They are a natural experiment showing us what happens when a galaxy grows old in perfect peace, never experiencing the collisions that shape its cousins. Their very presence forces us to reconsider the rules of galaxy formation, proving that the cosmic web can create not just brilliant cities, but also vast, silent, and mysterious cathedrals in the dark. The deep silence of space holds the fossilized echo of the universe's first sound. In the first 400,000 years after the Big Bang, the cosmos was not a quiet void, but a seething, roaring ocean of plasma. Ordinary matter, in the form of protons and electrons, was married to light in a hot, opaque fog, and gravity was already beginning to pull the dark matter into the first faint threads of the web. Within this dense medium, a titanic struggle was underway. Gravity, pulling matter inward, fought against the immense outward pressure of radiation. This created a series of pressure waves, colossal ripples that raced through the primordial soup at more than half the speed of sound. These were the baryon acoustic oscillations, the first and largest sound waves in existence. Each wave was a spherical shell of compressed matter, a density wave propagating outwards from every single slight overdensity that existed in the infant universe. Then, in a cosmic instant, everything changed. The universe expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. In what is called recombination, the fog suddenly cleared. Light, which had been trapped, was set free, creating the cosmic microwave background we observe today. But the matter was left behind, frozen in place. Each of those spherical sound waves was instantly fossilized, leaving a distinct signature, a subtle, preferred distance between regions of higher and lower density. This distance, this standard ruler, is etched into the very fabric of the cosmic web. Today, when we create three-dimensional maps of millions of galaxies, we do not see a random scatter. We see that galaxies have a slight but statistically significant preference to be separated by this specific scale, about 500 million light-years. It is as if the universe is stamped with a cosmic barcode, a regular pattern imprinted from its earliest moments. This fossilized echo is not just a beautiful relic, it is one of the most powerful tools in cosmology. Because we know the true physical size of this standard ruler from our understanding of the early universe, we can measure how it appears stretched or compressed in our sky. By comparing its known size to its apparent angular size, we can calculate precise distances to galaxies across vast cosmic times. This allows us to chart the expansion history of the universe with breathtaking accuracy, completely independent of other methods like supernova. It is the cosmic web itself, with its imprinted memory of the first sound, that provides this fundamental measuring stick, deepening our understanding of dark energy and challenging us with puzzles like the Hubble tension. The silent web we see today is still vibrating with the echoes of a long-vanished roar. A galaxy's cosmic address dictates its destiny. The majestic spiral arms of the Milky Way, the smooth, featureless glow of a giant elliptical, these are not just random shapes. They are the direct result of a galaxy's location within the grand architecture of the cosmic web, and this environmental influence is our 19th mystery. Think of the web as a city with very different neighborhoods. In the dense, urban core of a galaxy cluster, the environment is chaotic and violent. Galaxies swarm together at incredible speeds like a bustling crowd in a metropolitan square. In this environment, close encounters are not just possible, they are inevitable. When two spiral galaxies swing too close to one another, their delicate structures are torn apart. Their gravitational fields intertwine, pulling long streams of stars into tidal tails and violently funneling gas into their central regions. This sudden influx of fuel can trigger a firestorm of new star formation, a starburst, and often ignites the supermassive black hole at the galaxy's core, turning it into a brilliant quasar. But this frenzy is short-lived. The multiple mergers, combined with the relentless gravitational harassment from neighbors, completely erase the galaxy's spiral identity. The ordered, rotating disk is shattered, and the stars are thrown into random, chaotic orbits, creating a smooth, round, or oval-shaped elliptical galaxy. It is a cosmic demolition and reconstruction project driven entirely by the crowded conditions of the cluster node. Now travel out to the suburban filaments. Here, the environment is calmer but still structured. Galaxies line up along these cosmic highways, moving at more sedate speeds. They are not completely safe from interactions, but the encounters are slower and more gentle. A small galaxy might be slowly cannibalized by a larger one, its stars absorbed to fatten the larger galaxy's disk, or a near miss might simply warp the spiral arms, creating a barred structure. This environment is the perfect nursery for preserving beautiful, orderly spirals like our own. The filaments provide a steady, cold flow of gas to keep star formation going, while the lower density of galaxies allows a spiral to maintain its delicate structure for billions of years. Finally, venture into the deep voids, the cosmic countryside. Here, a galaxy is an isolated island, without any neighbors to interact with, and with very little new gas falling in. Its evolution is governed by internal, slow processes. A void galaxy might start as a small spiral, but without mergers to transform it or fresh gas to renew its spiral arms, its star formation will slowly gutter out. It may never become a grand elliptical, instead aging into a small, faint, and often irregular shape, a quiet hermit in the vast emptiness. So, the next time you see an image of a galaxy, remember that its shape is not an accident. It is a storybook telling the tale of its life within the cosmic city, a life of violent collisions in the downtown core, of steady growth in the suburbs, or of quiet solitude in the rural void. This galactic neighborhood we call home may be far emptier than we ever suspected. Our Milky Way galaxy, along with its local group, appears to reside inside a vast cosmic bubble, a region of significantly lower density than the average universe. This is the KBC void, named for the scientists who proposed its existence, and its reality is the 20th profound mystery. If true, it means our cosmic address is not in a typical suburban filament, but in an immense and underpopulated rural zone. This local emptiness would have a profound effect on our cosmic perspective, like living in a valley and trying to gauge the average height of the surrounding mountains. The key issue is the expansion rate of the universe, the Hubble constant. One of the primary methods for measuring this rate locally relies on observing nearby supernova and other cosmic mile markers. But if we are sitting in a void, the gravitational landscape is distorted. The relatively weaker gravity inside our local bubble means that galaxies just outside its edge are being pulled away from us by the denser regions beyond, making it appear as if the universe is expanding faster in our local vicinity than it truly is on a global scale. This could provide a potential and deeply unsettling resolution to the Hubble tension. The discrepancy between the local and early universe measurements might not be a sign of new physics, but simply a cosmic illusion created by our unlucky position in a giant hole. It forces us to ask a humbling question. Are we not at a typical location in the universe, but instead residing in a special, underdense region that skews all our local observations? The Copernican principle, the idea that we do not occupy a privileged place in the cosmos, is thrown into doubt. Confirming the KBC void is incredibly difficult, as it requires mapping the three-dimensional distribution of millions of galaxies around us to see if this local underdensity is real and as vast as proposed. The mystery of our cosmic address challenges the very foundation of modern cosmology, suggesting that the most fundamental number we use to describe the universe's expansion might be a local mirage, a trick of the light played by the empty space around our galactic home. The scale of the cosmic web can defy comprehension, but one structure in particular pushes the limits of what we thought was possible. Known as the Hercules Corona Borealis Great Wall, this colossal filament is a congregation of galaxies so vast it stretches for an incredible 10 billion light-years across the cosmos. To put that in perspective, if you could travel at the speed of light, it would take you longer to cross this single structure than the current age of our planet Earth. Its discovery sent shockwaves through the world of cosmology because, according to our most trusted models, such an immense object should not exist. The principle of homogeneity, the idea that the universe is smooth on the largest scales, suggests there is a fundamental size limit to any structure. This limit is set by the age of the universe and the speed at which information, including gravitational influence, can travel. Nothing can coordinate matter over a distance larger than the universe is old, because there simply has not been enough time for any signal, even gravity, to cross that void. The Great Wall appears to violate this cosmic speed limit. How could gravity have possibly assembled something so enormous in only 13.8 billion years? One possibility is that our standard model of cosmology, the lambda cold dark matter model, is missing a crucial ingredient. Perhaps dark energy behaved differently in the distant past, or the initial seeds from inflation were not as random as we assume, containing pre-existing correlations on scales we are only now beginning to see. Another, more speculative idea is that the Hercules Corona Borealis Great Wall is not a single, coherent structure in the traditional sense, but a chance alignment of several smaller filaments along our line of sight, a cosmic illusion of perspective that makes separate threads appear woven into one unimaginably large tapestry. Distinguishing between these possibilities is one of the great challenges of modern astronomy, requiring ever more precise maps of the distant universe. The existence of such a giant forces us to confront the humbling notion that our cosmic maps are still incomplete, and that the true architecture of reality may be grander and more mysterious than our theories have yet dared to predict. Our cosmic neighborhood feels strangely empty. The vast halo of dark matter surrounding our Milky Way should be teeming with hundreds of small, faint satellite galaxies, ancient remnants from the epoch of structure formation. Yet when we look up, we find fewer than 60. This glaring mismatch between prediction and observation is the long-standing missing dwarf galaxy problem, and its solution lies deep within the fractal substructure of the cosmic web. The most sophisticated computer simulations of our universe, which model the gravitational pull of cold dark matter with stunning precision, paint a very specific picture of galaxy formation. They show that large galaxies like our own should have been built from the bottom up through the relentless merging of thousands of smaller protogalactic clumps. The gravitational ghosts of these ancient building blocks, the simulations tell us, should still be orbiting us today as a vast swarm of dwarf galaxies. Their absence in our telescopes is a crisis for our most fundamental models. Have we misunderstood dark matter itself? One compelling possibility is that we have not, but that our eyes are simply not sharp enough. These smallest dark matter halos may indeed exist in their predicted thousands, but they are so faint that they contain very few or even zero stars. They would be dark galaxies, invisible halos of pure matter drifting silently through the galactic night. The key to their darkness lies in the physics of star formation. For a gas cloud to collapse and ignite new stars, it must be able to cool down, shedding its gravitational energy. In the smallest halos, the gravitational pull is simply too weak to compress the gas effectively. Furthermore, the fierce ultraviolet radiation from the first stars and galaxies could have heated the primordial gas, preventing it from ever falling into these tiny halos in the first place, sterilizing them of starlight from the very beginning. This idea of dark, starless halos elegantly preserves our core model of dark matter while explaining the empty skies, but there is another, more violent solution. Perhaps the dwarfs did form but were torn apart. The early universe was a chaotic place, and the relentless tidal forces from the growing Milky Way could have shredded these fragile satellites long ago, leaving behind only the faintest streams of stars as their ghostly tombstones. Astronomers are now hunting for both the missing starlight and these stellar streams, using ever more sensitive sky surveys. Every new, ultra-faint dwarf galaxy discovered and every stellar stream mapped is a vital piece of this cosmic puzzle. The missing dwarfs are not just a counting error, they are a direct probe into the most minute scales of the cosmic web, testing our understanding of how the very first sparks of light learn to ignite in the darkness. These invisible halos are not just formless clouds. Each one possesses a hidden architecture, a specific pattern of density that holds the key to the identity of dark matter itself. This brings us to the 23rd great mystery, the nature of dark matter halos. For decades, our best simulations have predicted a very specific internal structure for these halos. They should be densest at their very centers, with a concentration of dark matter rising steeply inward in what is known as a cusp. Picture a mountain with an incredibly sharp, pointed peak. This cuspy profile is a direct prediction of the leading model, where dark matter is cold and collisionless, meaning its particles pass right through each other without interacting. But when astronomers look at the real universe, particularly at the motions of stars within small, faint dwarf galaxies, they often find a puzzling contradiction. The data frequently suggests that the dark matter density in the core of these halos is much flatter, more like a rounded hill than a sharp peak. This is the core versus cusp problem, and it is one of the most persistent headaches in modern cosmology. If the halos truly have soft cores instead of sharp cusps, it implies that our basic understanding of dark matter is flawed. Perhaps dark matter is not completely cold and collisionless. Maybe these particles can interact with each other through some unknown force, a kind of dark version of electromagnetism. These self-interactions would allow the particles to bounce off one another in the crowded galactic center, effectively smoothing out the sharp cusp into a gentler core, much like shaking a bag of marbles will settle them into a smoother pile. Or perhaps the answer lies not with dark matter, but with the ordinary matter we understand. The incredible energy released by supernova in the early universe could have blown vast winds, violently sloshing the galactic gas back and forth. This ordinary matter, churning within the heart of the dark matter halo, could have acted like a spoon stirring a cup of tea, gravitationally dragging the dark matter outward and eroding the central cusp. The core versus cusp debate is far from settled. Some galaxies show cusps, others show cores, and the reason for this discrepancy is itself a deep mystery. Is it a question of a galaxy's mass, its history, or its environment within the cosmic web? Unlocking the true density profile of these halos is like getting the first clear fingerprint of a ghost, a vital clue that will finally tell us what the dominant material in our universe is actually made of. The silent architecture of the cosmos has just begun to whisper in a new frequency. Astronomers have recently unveiled a hidden layer of the cosmic web, not with optical or X-ray telescopes, but by tuning into the universe's radio symphony. Stretching between colossal galaxy clusters are immense, faint bridges of radio emission, glowing filaments so vast they defy easy explanation. These are not the gentle glow of starlight or the hot breath of galactic gas. They are the signature of something far more energetic, tracing the cosmic scaffolding in a light we had never seen before. What could possibly illuminate the empty highways between clusters with such a pervasive, if faint, radio glow? The prime suspects are electrons, but not just any electrons. These are relativistic electrons, particles whipped to nearly the speed of light, spiraling along magnetic field lines that are themselves woven through the cosmic filaments. As these ultra-fast electrons twist and turn in the magnetic field, they emit synchrotron radiation, a specific type of radio wave. It is the same process that creates the beautiful radio lobes around active galaxies, but here it is happening on a scale of unimaginable grandeur, in the near-perfect vacuum between clusters. But this presents a monumental puzzle. How do these electrons get accelerated to such fantastic speeds in the first place, in regions of space that are supposed to be quiet and uneventful? One compelling theory points to the violent history of the web's own formation. As galaxy clusters grew over billions of years, they did not simply assemble peacefully. They collided and merged in the most energetic event since the Big Bang. These colossal mergers create immense shock waves that ripple through the intergalactic medium, cosmic tsunamis traveling through the filaments. These shocks could act as natural particle accelerators, far larger than any human-built machine, capable of giving electrons the tremendous kick needed to make them glow in radio waves. Another possibility is that the turbulent motions of gas within the filaments themselves, stirred over eons by galactic winds and active black holes, generate enough sustained turbulence to keep a population of electrons energized. Or perhaps the magnetic fields threading the voids are far stronger than we ever suspected, providing the necessary intensity for the synchrotron process to work even with a weaker flow of particles. The discovery of these cosmic radio bridges is more than just finding a new type of light in the darkness. It is a direct window into the most energetic and dynamic processes shaping the universe's largest structures. It suggests that the cosmic web is not a static relic, but a living, breathing system, coursing with energy and animated by a history of cosmic violence we are only now beginning to perceive. This quiet symphony of creation was not perfectly tuned. In the first 20 minutes of the universe, during a fleeting epoch known as Big Bang nucleosynthesis, the primordial cosmos forged the lightest elements. As the universe expanded and cooled from its initial inferno, protons and neutrons began to fuse, creating the nuclei of hydrogen, helium, and a tiny, trace amount of lithium. This was the moment the periodic table was born, with only 3 entries. The calculations for this process are exquisitely precise, grounded in our well-tested understanding of nuclear physics. The predicted amounts of hydrogen and helium match the ancient, observed abundances in nearly pristine gas clouds with stunning accuracy, a triumphant confirmation of our Big Bang model. But there is a glaring exception, a single note that rings false. The amount of lithium-7, the main isotope, is a problem. Our theories predict there should be about 3 times as much lithium in the oldest stars as we actually find. It is not a small discrepancy, it is a factor of 3, a cosmic deficit that has persisted for decades. This is the lithium problem, and it points to a fundamental gap in our knowledge of the universe's first moments. How could the nuclear recipe be so perfectly correct for hydrogen and helium, yet so wrong for this one fragile element? The initial conditions of the cosmic web, the distribution of matter that would one day form the vast filaments, depended entirely on the physics of this first 3 minutes. If our understanding of that physics is incomplete, then the very seeds of the cosmic structure we see today were planted by a process we do not fully comprehend. Perhaps unknown particles, like certain types of dark matter, were present and interfered with nuclear reactions, destroying lithium as it formed. Or maybe our models of stellar interiors are flawed, and these ancient stars are somehow burning their surface lithium away over billions of years. Another, more radical idea is that the primordial gas was not perfectly mixed, and the pockets that formed the first stars were systematically depleted in lithium from the very beginning. Whatever the cause, this tiny anomaly is a massive clue. The lithium problem is a whisper from the universe's first nuclear furnace, telling us that the story of creation is missing a page that holds the key to the initial conditions that gave rise to everything, from the smallest atom to the largest filament in the cosmic web. That fragile lithium problem is a ghost from the universe's first moments, but a far larger ghost haunts the cosmos today. Nearly half of the ordinary matter that should exist is simply missing, a galactic accounting error known as the missing baryon problem. The prime suspect for this cosmic hideout is not some distant dimension, but the very fabric of the cosmic web itself, in the form of an elusive fog called the warm-hot intergalactic medium, or WHIM. This is not a gas you could ever see or feel. It is a tenuous, superheated plasma woven through the filaments, so incredibly diffuse that a single cubic meter of it might contain only a few atoms. Finding this WHIM is the astronomical equivalent of trying to spot a wisp of steam in a darkened cathedral using only a faint flashlight. Yet its discovery would solve one of cosmology's most persistent puzzles. So how do you hunt for something so perfectly transparent? Astronomers have become cosmic detectives using the universe's own flashlights. When the brilliant, piercing light from a distant quasar travels for billions of years to reach our telescopes, it passes directly through these cosmic filaments. The specific gases in the WHIM, heated to millions of degrees, absorb very particular colors or wavelengths of that brilliant light. This leaves behind a unique fingerprint, a series of faint, dark lines in the quasar's spectrum, like finding a specific set of chemical fingerprints at a crime scene. But the signal is incredibly weak, easily drowned out by other sources. Another method is to look for the WHIM's own faint glow. At such extreme temperatures, the gas should emit a soft whisper in X-ray light. Space-based X-ray observatories like the Chandra X-ray Observatory and XMM Newton are essentially giant listening devices tuned to hear this cosmic hum. They scan the regions between massive galaxy clusters where filaments are thought to connect, searching for that telltale, diffuse X-ray glow that would betray the presence of this hot, hidden ocean of matter. The challenge is immense, as the signal is often fainter than the background X-ray noise of the entire sky. Each tentative detection is a major victory, a piece of the puzzle falling into place, confirming that the missing atoms are indeed there, hiding in plain sight, woven into the vast, hot tapestry of the cosmic web. Solving this mystery completes the inventory of our cosmic home, finally telling us the final whereabouts of the ordinary matter that builds everything we know, from the tallest mountain to the farthest star. The cosmic web is a stage for the most violent collisions in the universe. Deep within its dense nodes, entire galaxy clusters, each containing thousands of galaxies, are crashing together in a spectacle of pure cosmic power. These are not slow, graceful encounters, but cataclysmic events that release more energy than a billion supernovae, and they provide our clearest natural laboratory for studying the ghostly presence of dark matter. The most famous of these cosmic train wrecks is the Bullet Cluster, a system where two galaxy clusters have slammed into one another at millions of miles per hour. When astronomers first observed this collision, they expected to see a tangled mess of matter. Instead, they saw a revelation. By mapping the cluster in multiple ways, they pieced together a story that forever changed our view of the cosmos. First, they used X-ray telescopes to see the hot gas, the ordinary baryonic matter that makes up most of a cluster's visible mass. This gas, behaving like a fluid, was slowed dramatically by the collision, creating a bullet-shaped shock wave between the two clusters. Then, they used a technique called gravitational lensing to map the total mass, both visible and dark. This technique measures how the cluster's gravity bends the light from more distant galaxies, acting like a cosmic scale. The result was stunning. The peak of the total mass, the heart of the gravitational field, was not where the hot gas was. It had sailed right through the collision, leaving the ordinary gas behind. This was the first direct, bulletproof evidence that most of the matter in the universe is not only dark, but fundamentally different from the atoms we know. The dark matter, whatever it is, did not slow down in the crash. It did not interact with itself or the gas in any way except through gravity. It simply passed through, ghost-like and unscathed, proving its collisionless nature. This single observation ruled out entire classes of theories about dark matter. It could not be made of normal particles that interact strongly, or it would have been trapped in the wreckage with the hot gas. The bullet cluster showed us the invisible skeleton of the cosmos in the most dramatic way possible, revealing a universe where the stuff that builds the web is fundamentally alien to the stuff that builds us. Every new cluster merger we discover is another chance to test the rules of this dark universe, probing the nature of the cosmic scaffold with the most powerful collisions since creation itself. The sheer scale of the cosmic web forces us to ask a question bordering on philosophy. What is the total amount of information, the cosmic data, required to describe this entire magnificent structure? This leads us to a mystery so profound it challenges our very conception of reality, the possible connection between the cosmic web and the holographic principle. At its heart, this radical idea suggests that our three-dimensional universe, with all its galaxies, stars, and planets, might be a projection, a hologram encoded on a distant two-dimensional surface. Think of a credit card hologram, a flat sticker that creates the illusion of a three-dimensional image floating in space. The holographic principle proposes that our reality might be a similar, albeit vastly more complex, projection. The information describing everything within a volume of space, including every twist and turn of every cosmic filament, could be entirely contained on its boundary, like a cosmic movie being projected from the walls of the universe. So what does the intricate complexity of the cosmic web tell us about this? The web's staggering detail, the specific location of every galaxy cluster and every wisp of gas in a filament, represents an immense amount of information. If the holographic principle is correct, then all this information must be encoded on the universe's theoretical boundary. The web's vastness and fine structure could be a direct reflection of the maximum information capacity of that lower dimensional surface. It is as if the universe's hard drive has a finite size, and the cosmic web is the most complex, data-rich structure it can possibly display. This is not just a wild speculation. It emerges from our studies of black holes, where physics seems to demand that all information falling into a black hole is somehow encoded on its two-dimensional event horizon. The holographic principle simply applies this logic to the entire cosmos. The cosmic web, in this view, becomes more than just a structure. It is the ultimate expression of cosmic information, a three-dimensional visualization of data stored on the universe's fundamental shell. While this remains a highly theoretical frontier, the very existence of the web, with its specific patterns and immense complexity, challenges us to consider that the true nature of reality might be written not in the volume of space, but on its distant, invisible edges. Drifting in the blackness between galaxies is a ghostly light. Within the dense nodes of the cosmic web, where thousands of galaxies swarm in a crowded metropolis, astronomers have detected a faint, pervasive glow. This is not the concentrated light of a single galaxy, but a diffuse, ethereal luminescence that fills the entire space between them. We call this mysterious phenomenon intracluster light, and it is the collective shine of countless orphan stars, stellar castaways that have been ripped from their galactic homes and left to wander the intergalactic void. How did these stars become so lost, and what can their lonely light tell us about the violent history of the cluster itself? The answer is written in the relentless gravity of the cosmic web. In the crowded environment of a cluster, galaxies are constantly swinging past one another at tremendous speeds. During these close encounters, their gravitational fields act like cosmic tidal forces, pulling and stretching them. The stars on the outer fringes of a galaxy, held by a weaker gravitational grip, are the most vulnerable. They can be easily plucked away like grapes shaken from a bunch and flung out into the emptiness between galaxies. This process, known as tidal stripping, is a primary source of this lost stellar population. But there is an even more violent mechanism. When two galaxies collide and merge, a spectacularly chaotic event, their structures are completely torn apart. In the resulting gravitational turmoil, millions, even billions of stars can be ejected from the newly forming galactic core, condemned to a permanent existence in the dark intercluster medium. The distribution of this faint light is not random, it is a fossil record of the cluster's assembly. By mapping its delicate glow, astronomers can trace the history of past interactions and mergers. The light often forms faint streams and bridges between galaxies, marking the paths of ancient collisions and cannibalism. In a very real sense, the intracluster light is the cluster's ghost, a luminous echo of all the violence and drama that built it over billions of years. The sheer brightness of this light is an anomaly that holds further clues. It is far more luminous than our simplest models predicted, suggesting that the process of galaxy disruption within clusters is more efficient and ongoing than we ever imagined. These orphan stars are not a minor detail, they are a fundamental component of the cluster's mass and history. Their pervasive glow forces us to see these cosmic cities not as collections of isolated islands, but as a single, dynamic ecosystem where stars are continually exchanged and redistributed in a grand gravitational dance. The ghost light between the galaxies is a direct, visible testament to the construction of the cosmic web, a shimmering residue of the chaos that built the universe's grandest structures. Even the faintest glow from the cosmic dawn holds a secret direction. Deep within the most precise maps of the cosmic microwave background, the universe's first light, some scientists claim to have found a ghostly alignment so strange it has been dubbed the axis of evil. This is not a malevolent force, but a deeply puzzling pattern. The hot and cold spots in that ancient radiation appear to be subtly correlated with the plane of our own solar system and the direction of our galaxy's spin. It is as if the universe's baby picture has a faint watermark that points directly back at us, which, according to everything we believe, should be impossible. The cosmological principle, the bedrock of modern cosmology, insists the universe has no center and no preferred direction. It should look the same in all directions, a perfectly isotropic cosmos. The axis of evil suggests otherwise. It hints at anisotropy, a fundamental lopsidedness to reality on the grandest scale. If this alignment is real, and not a statistical fluke or a subtle error in data processing, its implications for the cosmic web are staggering. The web itself, the vast architecture of filaments and voids, might not be randomly oriented. Its grand design could have a tilt, a preferred axis imprinted from the very beginning. This would mean that the gravitational forces that sculpted the web did not pull equally in all directions, but had a slight bias, a cosmic grain, like the texture in a piece of wood. The initial seeds for the filaments and voids would have been sown with a directional preference, potentially influencing how galaxies spin and how clusters align across billions of light years. The controversy is fierce. Is the axis of evil a real feature of the universe, or are we simply seeing patterns in the noise, a celestial mirage created by our own limited perspective? The answer cuts to the core of our cosmic arrogance. Do we live in a special place, a location that just happens to be aligned with the universe's fundamental geometry? Or is this the first tantalizing clue that the universe is not what we thought, that its smooth, featureless facade hides a deeper directional structure, a fundamental anisotropy that guides the growth of the cosmic web itself? The violent hearts of galaxies hold a power that shapes the cosmic web itself. A supermassive black hole, when it actively feeds, becomes an active galactic nucleus, or a cosmic engine of unimaginable ferocity. As matter spirals into the black hole's gravitational abyss, it forms a searingly hot accretion disk, and the system often blasts out colossal jets of radiation and particles that can pierce through intergalactic space for millions of light years. This is not a destructive force in the simple sense. It is a cosmic regulator, a feedback mechanism of breathtaking scale. The energy pouring from an AGN acts like a cosmic thermostat for star formation. When a galaxy is forming stars too quickly, the resulting turbulence can funnel vast amounts of gas directly toward the central black hole, switching on the AGN. The resulting outburst then heats the surrounding gas, or even blows it entirely out of the galaxy, shutting off the very fuel supply for new stars. It is a self-regulating cycle, preventing galaxies from growing too large too fast. But the influence of these active hearts does not stop at the galactic border. Their powerful jets drill far out into the cosmic filaments, injecting energy and heat directly into the intergalactic medium. This AGN feedback is thought to be the primary reason why the gas in the largest galaxy clusters remains so hot, preventing it from cooling, collapsing, and forming a riot of new stars that would otherwise exist. This process is crucial for maintaining the cosmic web we see today, yet it remains one of the least understood aspects of galaxy evolution. The timing, the power, and the precise mechanics of this feedback are a constant source of mystery. Why do some AGN outbursts seem to quench star formation entirely, while others appear to trigger it? How exactly does the energy from these relativistic jets get transferred to the diffuse gas of the web? We are witnessing the universe's method of balancing its own growth, a dramatic cycle of creation and suppression orchestrated by the most violent objects in existence. A sudden, brilliant flash of radio energy appears in the depths of space, lasting less time than the blink of an eye. These are fast radio bursts, and their incredible power is matched only by their profound mystery. For a few milliseconds, a single burst can outshine an entire galaxy, and then it vanishes without a trace. While their origins are a cosmic puzzle in themselves, these fleeting signals are now becoming one of our most powerful tools for illuminating the cosmic web's darkest secrets. Each burst is a cosmic lighthouse, and its light must travel across billions of light years to reach us. On that immense journey, it passes through the vast, invisible filaments of the web, encountering the diffuse gas and the magnetic fields that permeate these cosmic highways. This encounter leaves a unique mark on the signal. The higher frequency radio waves arrive at our telescopes just a fraction of a second before the lower frequencies, a delay caused by the charged particles in the gas the burst traveled through. This delay, known as the dispersion measure, is like a cosmic odometer. By measuring it, astronomers can count the total number of free electrons the burst encountered along its path, effectively weighing the amount of ionized gas it passed through. This is a direct probe of the elusive warm hot intergalactic medium, the very missing baryons we have been searching for. If we can pinpoint the galaxy that a burst came from, we know its exact distance. Then, by subtracting the known amount of gas within that host galaxy and its immediate surroundings, we are left with a measurement of the material in the cosmic web itself, the tenuous fog stretching across the void. A single burst gives us a single, precise line of sight. But with hundreds of these bursts now being detected, we are building a vast network of cosmic probes, crisscrossing the universe and sketching out the distribution of matter in the filaments between galaxies. Some bursts even show the twisted signature of Faraday rotation, a subtle effect indicating they have passed through powerful magnetic fields. This allows us to not only map the gas in the web, but also to measure the strength and structure of the magnetic fields woven through it. These mysterious millisecond flashes are transforming into the ultimate cosmic surveyors, using their brief, brilliant lives to trace the invisible architecture of our universe, one filament at a time. This fractal pattern, this sense of looking at the same structure whether you zoom in or zoom out, is a profound clue about the forces that built the cosmos. If the cosmic web is a fractal, it would mean the processes that created it were scale invariant. The same set of physical rules would have operated with equal power on the very smallest scales and the very largest, from the quantum realm to the supercluster scale. This idea directly challenges the standard model of cosmology, which predicts that on the very largest scales, the universe should finally become smooth and homogeneous, losing its intricate web-like texture. The hunt for this fractal signature is a battle of statistics. Scientists analyze the three-dimensional maps of galaxy surveys, counting how many galaxies they find within cubes of space of increasing size. In a perfectly smooth universe, the number of galaxies would increase in a predictable, steady way as the cube gets larger. But in a fractal universe, the count would follow a different, more complex mathematical rule, one that reveals a repeating pattern of clusters within clusters, filaments within filaments, all the way down. The results from these immense cosmic censuses are tantalizing and deeply controversial. Some studies of older data did suggest the galaxy distribution was fractal, a never-ending cascade of structure. Other, more recent and precise surveys, like those from the Sloan Digital Sky Survey, indicate that the fractal pattern does indeed break down. On scales larger than about 300 million light-years, the universe appears to transition to a smoother, more homogeneous state. This is a crucial victory for the standard model, yet the debate is far from over. The transition point itself is a mystery. Why does the cosmos stop being fractal at that specific scale? The answer is written in the initial conditions of the universe, in the physics of inflation. The pattern of those primordial quantum fluctuations stretched across the cosmos imprinted a specific maximum scale for coherent structure. Finding that exact scale is like finding the fundamental grain of the universe, the pixel size of reality. If the web is not a perfect fractal, its self-similar nature on so many scales still tells us something beautiful and fundamental. It suggests that gravity, working on the random seeds from inflation, is a universal artist creating complex, branching patterns regardless of the starting size. It is the same force that shapes a tiny snowflake and a billion light-year-long filament of galaxies. This connection between the infinitesimally small and the astronomically large is one of the most elegant truths of our cosmos, a hint that the same simple rules govern the universe at every level of its magnificent existence. The ghostly halos predicted by our simulations may not always be empty. Could entire galaxies made almost entirely of dark matter be hiding in plain sight? This is the startling premise of the dark galaxy hypothesis, a concept that pushes our understanding of the cosmic web to its limits. These would not be mere starless clumps, but substantial structures, true galactic ghosts that somehow avoided the star-making process almost entirely. The most famous candidate is a cloud of gas known as Dragonfly 44. From its motions, astronomers deduced it possessed the mass of a giant galaxy like the Milky Way. Yet when they looked, they found it was desperately faint, a dim smudge containing less than 1% of the stars it should have. It appears to be a galaxy where the dark matter skeleton never managed to clothe itself in a luminous stellar body. How does such a thing even form? The answer likely lies in a uniquely quiet cosmic history. Perhaps these dark galaxies were born in the most barren outskirts of a cosmic filament, where the primordial gas was too spread out and never achieved the density needed to trigger efficient star formation. Or maybe they are cosmic fossils, systems that formed all their stars in a single, brief burst in the early universe and have simply faded into near darkness over the intervening billions of years. Another possibility is that they were stillborn, their gas sterilized by the fierce ultraviolet radiation from the first brilliant galaxies, preventing the collapse into stars before it could even properly begin. Finding these phantoms is among astronomy's greatest challenges. How do you see a galaxy that does not glow? Astronomers use a combination of cunning techniques. They scan the skies for vast, rotating clouds of neutral hydrogen gas that exhibit the gravitational signature of a massive dark matter halo, yet show almost no accompanying starlight. They also hunt for the subtle gravitational lensing effects, where the invisible mass of a suspected dark galaxy bends the light of a more distant star, creating a fleeting, telltale magnification. Each potential discovery is a monumental effort, a triumph of inference over direct observation. If dark galaxies are real and plentiful, they would solve the missing satellite problem elegantly, not by making the small halos dark, but by showing that even some larger halos fail to light up. They would represent an entire hidden population within the cosmic web, a shadow universe of structures that play by a completely different set of rules, forever altering our senses of the cosmic architecture. Our own galaxy is not adrift in a still sea. We are caught in a vast, silent river, pulled by a force we cannot see toward a destination we do not fully know. This is the mystery of the Great Attractor, a colossal gravitational anomaly hidden within the dense tapestry of the cosmic web, tugging our entire local group of galaxies on a mysterious journey. For decades, astronomers have mapped the motions of galaxies around us, and a clear, unsettling pattern emerged. Like iron filings drawn to a powerful magnet, thousands of galaxies, including our own Milky Way, are streaming toward a specific point in the constellation Centaurus, moving at an incredible speed of over 600 kilometers every second. The source of this immense pull was named the Great Attractor, but its true nature remained veiled, quite literally, by the dusty plain of our own galaxy. This zone of avoidance, as it is called, is like a cosmic blind spot, a dense shroud of gas and dust in the Milky Way that blocks our view of the universe beyond invisible light. For a long time, the Great Attractor was a ghost, a gravitational signature without a visible form. What could possibly possess enough mass to command such a vast flow of galaxies? The answer, it turns out, is not a single monstrous object, but an entire metropolitan center of the cosmic web. Peering through the cosmic dust with X-ray and radio telescopes, which can penetrate the obscuration, astronomers discovered that the Great Attractor is not the final destination, but a waypoint on a much larger journey. It is the core of our local supercluster, a gargantuan knot of galaxies known as Laniakea. This Hawaiian word meaning immense heaven perfectly describes this structure, a web of filaments spanning over 500 million light-years, containing the mass of 100 quadrillion suns. Our Milky Way resides on a remote suburban filament of this vast continent, slowly flowing down the gravitational slope toward the densest node, the Norma cluster, which sits at the Great Attractor's heart. Yet even this is not the end of the story. Our entire Laniakea supercluster, with the Great Attractor at its center, is itself in motion, pulled by an even greater gravitational force, the Shapley supercluster, the most massive concentration of matter in our observable cosmic neighborhood. So the Great Attractor is not a mysterious, unseen behemoth, but a landmark in a hierarchy of flows, a testament to the fact that the cosmic web is not static. It is a dynamic, flowing system where gravity from the largest structures dictates the motion of everything, from the smallest dwarf galaxy to the grand superclusters themselves. We are not still observers of the cosmos. We are passengers on a galactic raft, riding a current that has been flowing for billions of years, drawn by the invisible architecture of the universe itself. Deep within the cosmic web's first nodes, a temporal paradox was brewing. How could supermassive black holes with masses of billions of suns already exist when the universe was less than 1 billion years old? This is not just a question of size, but of time. A stellar mass black hole, the remnant of a single massive star, should take billions of years to grow to such a monstrous scale by steadily feeding on gas. Yet our telescopes see these behemoths shining as brilliant quasars in the infant cosmos, a clear sign they were already fully formed and feasting. The standard path of growth is simply too slow. It would be like finding a fully grown redwood tree sprouting from a crack in the pavement just days after the concrete was poured. The timeline does not add up. This forces us to consider two radical possibilities for these cosmic anomalies. The first is that the seeds for these black holes were not ordinary stars at all, but something far more massive from the very beginning. In the dense, pristine gas of the early cosmic filaments, vast clouds could have collapsed directly under their own weight, skipping the star formation stage entirely. Imagine a gas cloud so immense and unstable that it bypasses the process of fragmenting into stars and plummets directly into a gravitational abyss, birthing a black hole with a mass of tens of thousands of suns in a single catastrophic event. This direct collapse black hole would provide a colossal head start, a seed already so large it could gorge itself on the surrounding gas and reach supermassive proportions within the narrow window of time the early universe allows. The second, even more exotic possibility is that they are primordial. What if these black holes were not born from gas or stars at all, but were instead forged in the unimaginable densities of the universe's first second? Tiny quantum fluctuations in the fabric of spacetime during inflation could have created regions so dense they collapsed directly into black holes. These primordial black holes would have been sown across the cosmos like invisible seeds, with the largest ones naturally sinking into the deepest gravitational wells of the emerging cosmic web, the future nodes of galaxy clusters. There, they would have begun their feast immediately, growing in the dark for millions of years before the first stars ever flickered on. The true answer likely involves a combination of these paths, a frantic, chaotic race against time in the densest neighborhoods of the young cosmic web. Solving this mystery is not just about understanding black holes, it is about deciphering the very rules of construction in the early universe, a place where the normal pace of cosmic evolution was dramatically accelerated by the raw, concentrated power of the first structures. These silent magnetic filaments threading the cosmic web are more than just invisible fields. They are a galactic highway system for the universe's most elusive travelers. Cosmic rays are not rays of light at all, but atomic nuclei, mostly protons, hurtling through space at nearly the speed of light. They carry immense energy, millions of times more powerful than anything we can create in our largest particle colliders. For over a century, their origins have been one of physics' greatest puzzles. How does the universe accelerate individual particles to such fantastic energies? The answer appears to be woven into the violent architecture of the cosmic web itself. The same colossal shocks that illuminate radio bridges between galaxy clusters are also perfect natural particle accelerators. When two clusters collide, they create tsunami-like shock waves that travel through the magnetized filaments for millions of years. A single proton caught in the turbulent currents of these shocks can bounce back and forth across the wavefront countless times, gaining a little more speed with each pass until it is finally ejected like a bullet from a cosmic rifle, set on a random journey across the intergalactic void. But this journey is anything but straight. The very structure of the web dictates the path of these particles. The magnetic fields woven through the filaments, though incredibly weak, are immense in scale. As a charged cosmic ray enters one of these fields, it begins to spiral along the magnetic field lines, its path bent and twisted into a corkscrew. This means that by the time a high-energy cosmic ray finally reaches our detectors, it is impossible to simply trace its path backward to its source. Its origin point has been completely scrambled by billions of years of magnetic interference. It is like trying to find the source of a leaf that has tumbled down a winding, turbulent river. You know it came from somewhere upstream, but the specific tree is lost to you. This is the heart of the mystery. We are constantly bombarded by these cosmic messengers, each one a calling card from a cataclysm in the distant web. Yet their letters of introduction have been torn to shreds by the magnetic winds of intergalactic space. The most energetic cosmic rays must come from the most violent events, perhaps from active galactic nuclei where jets from supermassive black holes rip through space, or from the frenzied star formation in colliding galaxies. Some might even be the echoes of long-dead neutron stars or the aftermath of gamma-ray bursts. The cosmic web acts as both the accelerator and the obscuring veil, a labyrinth that creates these incredible particles and then hides their sources from our view. Solving this mystery requires us to become cosmic detectives, not by looking for the particles themselves, but by mapping the magnetic fields of the web and understanding the violent ecology of its densest nodes, hoping to one day decode the scrambled map that leads back to the universe's most powerful engines. This perfect lockstep between dark and ordinary matter might not be so perfect after all. A subtle but profound mystery is emerging from the heart of galactic collisions and the quiet flow of cosmic filaments, suggesting that the invisible skeleton of the universe and its luminous flesh may be moving at slightly different speeds. We have always assumed that dark matter and baryonic matter, the atoms that build stars and planets, are gravitationally wedded, moving together through space as a single entity. After all, gravity treats all mass the same, regardless of whether it is dark or light. Yet the most advanced computer simulations of the cosmic web are beginning to reveal a tiny but persistent lag. In the chaotic aftermath of a galaxy collision, the simulations show that the clouds of interstellar gas, the baryonic matter, can experience a kind of cosmic drag. This is not a drag from air resistance. Space is a near-perfect vacuum. Instead, it is a drag caused by the complex physics of the gas itself. When giant clouds of gas slam into each other, they create immense pressure, shock waves, and turbulence. This internal friction acts as a brake, slowing down the ordinary matter just a fraction more than the invisible dark matter, which, being collisionless, simply glides through the carnage completely unaffected. The result is a minuscule velocity offset, a parting of ways between the seen and the unseen. It is as if in a crowd of people running, those wearing heavy, wet coats begin to lag ever so slightly behind those who are unencumbered, their progress slowed by a force the others cannot feel. For decades, this was just a curious prediction of our models, too small to ever measure in the real universe. But now, observational evidence is starting to catch up. By studying the precise movements of gas and stars in distant galaxy clusters and comparing them to the gravitational lensing map of the dark matter, astronomers are hunting for this telltale lag. They are looking for places where the peak of the mass, defined by the dark matter, is not perfectly centered on the peak of the gas. Finding this offset would be a monumental discovery. It would be the first tangible evidence of a dynamic difference between dark matter and the ordinary world, a crack in the perfect mirror of gravity. It suggests that the cosmic web is not a static sculpture, but a fluid and complex system where different components, governed by different rules, interact in ways we are only beginning to perceive. If confirmed, this tiny velocity offset forces us to ask a deeper question. Is this drag the only effect, or could there be other, more exotic interactions between the dark universe and our own, hidden within the vast currents of the cosmic web? Drifting through the cosmic web is a galaxy that looks less like a pinwheel and more like a perfect smoke ring suspended in the void. Hoag's object is a stunning anomaly, a nearly perfect circle of brilliant blue young stars surrounding a calm, golden core with a profound gap of darkness between them. How does such a symmetrical, hollowed-out structure come to exist? The answer seems to lie not within the galaxy itself, but in the dynamic environment of the cosmic web it calls home. One compelling theory suggests a high-speed collision, a galactic hit and run of incredible precision. Imagine a smaller dwarf galaxy plunging directly through the heart of a larger spiral disk. The gravitational shockwave from this bullseye impact would send a ripple of dense gas and star formation propagating outward from the center, much like a stone dropped in a pond creates an expanding ring. The central region, having been violently stirred, would settle into a smooth, elliptical-like core, while the outer ring, lit up by the collision, would continue its expansion, leaving a clear gap in its wake. This cosmic car crash could forge a perfect ring from a chaotic encounter, but not every ring galaxy fits this dramatic story. Some, like Hoag's object, show no sign of a perpetrator, no obvious dwarf galaxy remnant fleeing the scene. This points to a second, more subtle sculptor, the continuous gravitational tides of the cosmic web itself. As a galaxy moves along a filament, it can experience a steady, stretching pull from the dark matter scaffolding around it. This persistent tidal force can slowly reshape a galaxy, potentially funneling gas to the outer edges to form a ring and starving the inner regions, all without a single violent collision. The existence of these rare, beautiful structures forces us to acknowledge that the cosmic web is not a static backdrop. It is an active participant, a dynamic environment where both sudden, catastrophic impacts and the slow, relentless pull of gravity work in concert to carve some of the universe's most mysterious and beautiful forms. The silent expansion driven by dark energy is described by a single number, the cosmological constant. Yet this number holds a discrepancy so vast it is often called the worst prediction in the history of physics. The energy contained in the vacuum of space, which we observe as dark energy, should theoretically be enormous. When we calculate the sum of all the quantum fluctuations, the virtual particles popping in and out of existence in every tiny cubic centimeter of the cosmos, the result is an energy density of an almost unimaginable magnitude. This theoretical vacuum energy should be one followed by 120 zeros larger than the delicate, gentle acceleration we actually measure. 120 orders of magnitude is a number so colossal it defies all analogy. It is the difference between the size of a single proton and the size of the entire observable universe, and then multiplied by that same scale again and again. This is the cosmological constant problem, and the cosmic web is the ultimate expression of this staggering fine-tuning. If the vacuum energy were just slightly larger, even by a tiny fraction, the repulsive force would have been so powerful that it would have blown the universe apart in the first instance after the Big Bang. Gravity would never have had a chance to pull matter together into the first filaments, the first galaxies, or the first stars. The cosmic web would never have formed, and the universe would be a cold, empty, and rapidly expanding void. Conversely, if the value was slightly smaller or negative, the universe would have collapsed back in on itself in a big crunch long before life could ever emerge. The fact that we exist to observe a universe filled with structure means the cosmological constant must be almost, but not perfectly, zero. This incredible fine-tuning forces a profound question upon us. Is our universe a statistical fluke, an astronomically unlikely lottery ticket drawn from a near-infinite multiverse of possibilities, most of which are barren and empty? Or does this impossibly precise number point toward a deeper law of nature, a symmetry or principle we have not yet discovered, that naturally forces the vacuum energy to cancel out to nearly nothing? The cosmic web, with its grand filaments and vast voids, is the direct result of this inexplicable balance. Its very existence is a constant, silent reminder that the force shaping the cosmos on the largest scale is a number that, by all rights, should not be. The cosmic web is not only a structure of immense voids and filaments, but also a gallery of the profoundly strange. Scattered across this vast architecture are forms that seem to defy random chance, shapes that eerily mimic the familiar. One of the most striking is a structure known as the Hand of God. This is a pulsar wind nebula, a cloud of energetic particles blasted out from a rapidly spinning neutron star. To our telescopes, it appears uncannily like a human hand reaching out into the cosmos, its glowing fingers stretching through space. Is this a miraculous sign or a simple trick of perspective? The most likely explanation is a fascinating interplay of physics and our point of view. The spinning pulsar at the heart of this nebula is shooting out a powerful wind of particles, and it is also moving through space at high speed. This motion, combined with the complex magnetic fields that shape the outflowing particles, could create that elongated, finger-like structure. From our specific vantage point billions of trillions of miles away, the alignment is just right to create this ghostly, hand-shaped apparition. It is a powerful example of pareidolia, the human tendency to see faces and shapes in random patterns, like seeing a man in the moon or a dragon in a cloud. Yet, the very existence of such a well-defined structure forces us to ask if there are unknown forces at work, processes that naturally prefer to create such ordered, complex forms in the chaos of space. The Hand of God is not alone. Astronomers have found other peculiar shapes, from a cosmic question mark to vast bubbles and shells that seem too perfect to be natural. Each one presents a puzzle. Are they all just perspective illusions, or could some be signs of astrophysical processes we have not yet discovered? These celestial Rorschach tests challenge our perception and remind us that the universe has a flair for the dramatic, crafting art from the raw, violent physics of stellar death and rebirth. The vast architecture of the cosmos may be more than a celestial map. It could be the ultimate conduit for life itself. This is the profound mystery of panspermia, the idea that life's ingredients, or even life itself, could travel between the stars. We often picture this as a random, desperate journey, a lonely spore drifting blindly through the interstellar void. But what if the journey is not random at all? What if the cosmic web provides a structured highway system, guiding and concentrating this biological material across unimaginable distances? The mechanism begins with violence. A massive asteroid impact on a living world like the early Earth can eject fragments of crust into space, pieces that might contain hardy, dormant microorganisms shielded within the rock. These lithopanspermia travelers become cosmic hitchhikers. Now, instead of drifting aimlessly, they enter the gravitational currents of the local cosmic filament. Just as the web's gravity channels flows of dark matter and gas, it can also influence the trajectories of these solid objects over millions of years. The filament acts as a gravitational funnel, a great river in space that gradually corrals this ejected material, increasing the chances that it will eventually be drawn into a new star system forming somewhere else along that same filamentary thread. The odds of a random rock from one solar system hitting a planet in another are astronomically low. But if both systems are embedded within the same dense filament of the cosmic web, their gravitational environments are connected. The same flows that deliver gas to form new stars can also nudge life-bearing rocks toward those nascent planetary systems. This turns a near-impossible journey into a plausible, though still immensely slow, process. The web does not just build galaxies, it could be weaving a connected biological network where life, once sparked, has a pathway to spread, not randomly, but along the predetermined architecture of the universe. It suggests that if life exists in one star system, its cousins may not be in a random direction, but waiting patiently along the same cosmic filament, nurtured by the same ancient gravitational currents. Are we, and every living thing we know, not just residents of a single planet, but citizens of an entire filament, part of a vast, interconnected biological structure that spans the galaxy? A galaxy's color tells the story of its death. Drifting within the crowded nodes of the cosmic web are vast collections of galaxies that glow with a dull, ruddy hue, their vibrant blue star-forming days a distant memory. Astronomers call them red and dead, and the process that creates them, quenching, is a slow cosmic murder mystery. Why do these galaxies, residing in the richest neighborhoods of the universe, have their star formation so completely and permanently shut down? The investigation points to three primary suspects, each a brutal consequence of a galaxy's dense environment. The first is a silent, insidious process called strangulation. A spiral galaxy like our own Milky Way relies on a steady inflow of fresh, cold hydrogen gas from the cosmic web to fuel new stars. But when a galaxy falls into the immense gravitational well of a galaxy cluster, that vital supply line can be severed. The galaxy continues to burn through its remaining reservoir of gas, but no new fuel arrives. It is slowly starved, its star formation rates plummeting over 1 billion years as it exhausts its last reserves. The galaxy's population of massive, hot, blue stars die first, leaving behind the longer-lived, cooler, redder stars to dominate the light. It is a death by cosmic isolation, a quiet fading away. A far more violent and immediate fate is ram pressure stripping. Imagine a galaxy flying at thousands of kilometers per second through the superheated plasma that fills the space between galaxies in a cluster. This intergalactic medium acts like a torrential wind. For the galaxy, its own store of cold gas is like a cloud of dust held in a fragile hand. The immense pressure of this headwind can simply blow that gas away, ripping the star-forming fuel right out of the galaxy's grasp. You can actually see the aftermath in some clusters, with long, ghostly tails of gas streaming out behind galaxies, the visible evidence of their lifeblood being stripped away in real time. This is not a slow starvation, but a rapid, traumatic amputation of a galaxy's future. But perhaps the most intriguing suspect operates from within. This is AGN feedback, the self-regulating cycle powered by the supermassive black hole at the galaxy's heart. As a galaxy's central black hole feeds, it can unleash titanic jets and winds of energy. This outburst heats the surrounding gas, preventing it from cooling and collapsing to form stars, or can even blow the gas entirely out of the galaxy. It is a cosmic thermostat that, once triggered, can permanently shut down the star-making factory. In the dense nodes of the web, where galaxies are constantly jostled and fed gas in chaotic bursts, this feedback can be pushed into overdrive, leading to a premature and final quenching. So which of these forces is the true killer? The evidence suggests it is rarely just one. A galaxy might first be strangled, losing its external fuel supply. Then, as it plunges deeper into the cluster, ram pressure stripping finishes the job, clearing out any remaining pockets of gas. All the while, its central black hole may flare up, ensuring that no new stars can ever ignite again. The red and dead galaxies are the silent tombstones in the cosmic graveyard, each one a testament to the harsh and unforgiving physics that govern the universe's most crowded places. Hidden within the brilliant glare of a distant quasar lies a forest of shadows. This is the Lyman Alpha Forest, a phenomenon that transforms the light of these cosmic beacons into a detailed map of the universe's hidden gas. When a quasar's light begins its billion-year journey to our telescopes, it is a full, continuous spectrum. But its path is not through empty space. It cuts directly across the cosmic web, through the countless filaments of neutral hydrogen gas that thread the void. Each wisp of this gas, each cloud and tendril, acts like a filter. It absorbs a very specific sliver of the quasar's light, a wavelength known as the Lyman alpha line. As the universe expands, the light from the quasar is stretched, and so too are the absorption lines imprinted upon it. Gas that is closer to us absorbs light at a slightly less stretched wavelength, while gas that is farther away, and thus from an earlier time, absorbs light that has been stretched more. The result is not one single dark line in the quasar's spectrum, but a veritable forest of them, thousands of individual absorption lines, each one a fingerprint from a different cloud of hydrogen at a different distance along the line of sight. It is as if we are looking at a single, incredibly bright street lamp through a dense, multi-layered fog, and by analyzing every single shadow and dimming in its light, we can reconstruct the exact structure of the fog itself. This forest of shadows is our most powerful tool for charting the cosmic web's gaseous skeleton. By studying thousands of quasars, we can build a three-dimensional tomographic map of the universe, revealing how the neutral hydrogen is distributed in vast, interconnected sheets and filaments, exactly as our models of the cosmic web predict. Each line in this spectral forest is a tree ring in the history of cosmic structure, telling us not only where the gas is, but how the universe has evolved from a smooth distribution to the intricate, webbed architecture we see today. Mapping the universe's largest structures requires a telescope of almost unimaginable scope. The Dark Energy Survey represents one of the most ambitious astronomical projects ever conceived, a monumental effort to photograph the sky with a 570-megapixel digital camera, one of the most powerful in the world. Its primary mission is to peer into the depths of the cosmic web and measure the subtle fingerprints of dark energy, the force that governs the universe's ultimate fate. But how do you measure something that is, by its very nature, invisible? The survey does not look for dark energy directly. Instead, it meticulously charts the positions and shapes of hundreds of millions of galaxies across 1/8 of the entire sky. This vast three-dimensional map of the cosmic web becomes a precision instrument for detecting dark energy's influence. The survey uses two primary techniques, both rooted in the web's architecture. The first is the measurement of baryon acoustic oscillations, those fossilized sound waves from the early universe that are stamped into the distribution of galaxies. By seeing how this standard ruler appears to change size at different cosmic epochs, scientists can track how the expansion rate of the universe has changed over billions of years, directly probing the push of dark energy. The second technique is even more subtle. It involves measuring the weak gravitational lensing of distant galaxies. As light from these far-off galaxies travels to us, it is subtly bent and distorted by the gravitational pull of all the matter, both dark and luminous, in the foreground cosmic web. This includes the immense filaments and voids it must pass through. By analyzing the tiny, coherent distortions in the shapes of millions of galaxies, the survey can literally weigh the cosmic web, creating a map of its total mass distribution. This mass map is then compared to the map of where the galaxies are. Any discrepancy reveals how the growth of the cosmic structure over time has been slowed or shaped by the repulsive force of dark energy. The initial results are both confirming and confounding. They strongly support the existence of dark energy, but the precise data also allows for rigorous tests of Einstein's theory of gravity on scales he could never have imagined. Could gravity behave differently across the vast emptiness of a cosmic void compared to the dense heart of a filament? The Dark Energy Survey is providing the data to ask these profound questions, using the cosmic web as its laboratory and the light of countless galaxies as its measuring tape. A galactic collision is not just an act of destruction, it is a moment of unexpected creation. When two immense spiral galaxies swing too close, their gravitational embrace does not merely tear them apart, it can hurl colossal streams of gas and stars out into the intergalactic void. Within these ejected tidal tails, something miraculous can happen. The densest knots within this cosmic debris can collapse under their own gravity, igniting new stars and giving birth to entirely new galaxies. These are tidal dwarf galaxies, and they represent a profound departure from the standard story of cosmic construction. Unlike every other galaxy we have discussed, these objects may form almost entirely from the ordinary baryonic matter ripped from the disks of their parent galaxies. They are potentially born without a significant dark matter halo of their own, challenging a foundational rule of cosmology. How can a galaxy, a structure held together by gravity, form and persist without the dominant, invisible glue of dark matter? The survival of a tidal dwarf galaxy becomes a race against time. Its initial cohesion comes from the gravitational pull of its own gas and stars, the material stolen from its parents. For a while, this may be enough, but as it orbits through the chaotic environment of its parent cluster, it faces immense threats. The gravitational tides from larger galaxies can easily rip it apart if it is not securely anchored. Without a massive, extended dark matter halo to act as a protective gravitational cocoon, a tidal dwarf is incredibly fragile, a soap bubble adrift in a storm. The mystery deepens when we try to confirm their dark matter content. By studying the motions of stars within these peculiar galaxies, astronomers can weigh them. In several compelling cases, the measurements suggest there is little to no extra, invisible mass holding them together. They appear to be exactly what they seem, islands of pure, ordinary matter. If this is true, their very existence is a cosmic paradox. They are living proof that galaxies can, at least temporarily, form without the dark matter skeleton we thought was essential. Their continued survival, however, remains an open question. Can they live long, stable lives, or are they merely ephemeral structures destined to be shredded by the same gravitational forces that created them? Each tidal dwarf galaxy we discover is a natural experiment, testing the absolute necessity of dark matter and revealing a more complex and creative universe where even the most violent collisions can sow the seeds for new star-filled islands in the dark. The cosmic web's grand design may be a shadow cast from another dimension. To understand the fabric of space-time that underpins this entire structure, we must descend to the most fundamental level of reality, where the rules of the very large and the very small violently clash. General relativity gives us gravity as the elegant curvature of space-time, a force that sculpts the cosmic web. Quantum mechanics gives us the probabilistic, fuzzy world of particles, the realm that spawned the web's initial seeds. Yet these two pillars of physics are fundamentally incompatible. Uniting them into a single theory of quantum gravity is the greatest challenge in modern physics, and the cosmic web might be the key that finally unlocks it. The leading candidate for such a theory is string theory, which proposes a breathtaking idea. The fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy, smaller than a proton by a factor of trillions. Just as different vibrations of a violin string create different musical notes, the distinct vibrational patterns of these strings give rise to every particle in existence, from the photons carrying light to the quarks inside atoms. But here is the profound twist that connects to the cosmic web. For the math of string theory to work, the universe cannot have only the three spatial dimensions we experience. It requires extra, hidden dimensions, curled up into shapes so minute we can never perceive them directly. The specific geometry of these hidden dimensions would determine the properties of the strings vibrating within them, which in turn would dictate the fundamental constants of nature, like the strength of gravity or the mass of an electron. This is where the cosmic web enters the picture. The specific pattern of filaments and voids we see today, the precise strength of gravity that pulled it all together, and the nature of those primordial quantum fluctuations, all of these could be a direct consequence of the geometry of these hidden dimensions. The cosmic web, in this view, is not just a structure in space, it is a physical manifestation of the universe's deepest mathematical architecture. Another radical approach, loop quantum gravity, suggests a different kind of fabric. It proposes that spacetime itself is not smooth and continuous, but is woven from a network of discrete, finite loops, a literal fabric of a billion tiny intersecting threads. The cosmic web of galaxies, with its nodes and filaments, could be a macroscopic echo of this fundamental, quantized spacetime network. Are we, on the largest scales, simply seeing the underlying pixelated structure of reality itself? The quest for quantum gravity forces us to confront the origin of spacetime. Did the cosmic web's spacetime fabric simply unfurl from the Big Bang, or was it born from a quantum leap from nothingness, a cosmic phase transition where gravity itself crystallized into existence? The answers are hidden within the web's vast geometry, waiting for a theory that can read the universe's original blueprints. Our cosmic models predict a universe teeming with giant dwarf galaxies, but our telescopes see only darkness. This is the too big to fail problem, a direct challenge to our understanding of how galaxies form within their dark matter cocoons. The most advanced computer simulations show us a very specific picture of cosmic construction. They reveal that a large galaxy like our Milky Way should be surrounded by a swarm of massive dark matter subhalos, the gravitational ghosts of ancient building blocks. These are not the tiny, faint specks we struggle to see, but substantial structures, halos so massive and gravitationally powerful that they should have easily captured vast amounts of gas and lit up with billions of stars. According to every rule of galaxy formation we know, these subhalos are too big to fail at becoming brilliant dwarf galaxies. Yet when we look out at our local galactic neighborhood, these predicted giants are conspicuously absent. The space around us is far emptier than the simulations say it should be. It is as if we predicted a bustling metropolis of skyscrapers around a central city, but when we look, we find only a few scattered villages and mostly empty land. So where did all the skyscrapers go? The solution is not that the dark matter is missing. The halos are almost certainly there. The failure is in the lighting. Something prevented these massive halos from becoming luminous galaxies. One compelling idea points to the brutal environment of the early universe. The first stars and galaxies flooded the cosmos with fierce ultraviolet radiation, a background that heated the primordial gas, making it too energetic to fall into the gravitational wells of even these large subhalos. They were starved of fuel before they could even begin. Another possibility involves the very galaxy they orbit. As a sub-halo swings close to the Milky Way on its long, elliptical orbit, our galaxy's immense gravity can strip away its gas, a process called tidal stripping. A halo might make several passes, each time having its potential star-forming material ripped away, leaving it a dark, barren structure. There is also the dramatic influence of the cosmic web itself. The reionization of the universe, that great flash of transparency, may have occurred at just the right time and intensity to permanently sterilize these specific halos, preventing the collapse of gas within them. The too big to fail problem forces a profound shift in our thinking. It tells us that dark matter alone is not enough to make a galaxy. The luminous universe we see is not a perfect mirror of the dark matter scaffolding. It is a filtered version where the violent history of cosmic evolution, from the first starlight to the gravitational tides of larger galaxies, has acted as a cosmic curator, deciding which dark matter structures get to glow and which must remain forever in the dark. This is not a flaw in the dark matter model, but a crucial clue about the complex and often unforgiving physics of galaxy formation itself. Our universe's first light holds a subtle but profound crack in its symmetry. The cosmic microwave background, that near-perfect echo of the Big Bang, is not perfectly uniform across the entire sky. When scientists subtract the overall motion of our solar system through space, a faint but persistent temperature difference remains, a slight but significant asymmetry between one celestial hemisphere and the other. One half of the sky appears, on average, ever so slightly warmer than the opposite half. This is the CMB dipole, and it is a direct challenge to the cosmological principles demand for isotropy, the idea that the universe should look the same in every direction. If this asymmetry is not an illusion caused by our own motion, what could it possibly mean? One extraordinary explanation is that this dipole is a gravitational shadow, cast by an immense concentration of mass lying far beyond our observable horizon. We could be witnessing the pull of a supercluster, a structure so vast and massive that its gravity is tugging on our entire local group of galaxies, creating a temperature imbalance in the ancient light we receive. This would mean the cosmic web we have mapped is merely a local neighborhood, and the true architecture of the cosmos extends into realms of structure we cannot directly see, their gravitational influence reaching across the void to imprint a direction upon our sky. Another, more unsettling possibility is that the asymmetry is primordial, woven into the fabric of the universe from its very first moments. The initial conditions of inflation, the process that seeded all structure, may not have been perfectly uniform. There could have been a fundamental lopsidedness, a cosmic grain that set a preferred direction for the entire universe. If true, this would mean the universe has a fundamental axis, a grand north and south defined at the moment of creation, and the cosmic web itself grew with a subtle tilt we are only now detecting. Are we living in a universe with a built-in direction, a fundamental anisotropy that guides the growth of every filament and void? The mystery of the CMB hemispherical asymmetry forces us to question whether we reside in a truly isotropic cosmos or if the universe, on its grandest scale, has a preferred direction, a hidden alignment written in its oldest light. The final and most speculative mystery forces us to look beyond the very edges of reality itself. Could our magnificent cosmic web, with all its intricate filaments and vast voids, be utterly unique? Or is it merely one of an infinite number of variations in an immeasurably vast multiverse? This idea emerges from the leading theory of the universe's explosive beginning, cosmic inflation. This period of hyper-expansion may not have been a single, one-time event. Instead, it could be eternal, a process that continually spawns new, self-contained universes, each with its own random set of physical laws and constants. In most of these bubble universes, the conditions would be wildly different from our own. The strength of gravity might be too weak to pull matter into filaments, or dark energy might be so strong it tears any structure apart instantly. In those realms, cosmic webs never form, and the universe remains a dark, empty, or chaotic soup. Our universe, then, is the cosmic lottery winner. The specific, seemingly fine-tuned values of its fundamental forces allowed gravity to work just slowly enough and dark energy to emerge just late enough for the grand architecture we see to patiently assemble over billions of years. But if the multiverse is real, could we ever find evidence for other cosmic webs? The answer lies in looking for scars. If our universe collided with another bubble universe in the distant past, the impact would have left an imprint on the cosmic microwave background, a bizarrely cold or hot spot that defies all other explanations, much like the cold spot we have already detected. Finding such a bruise on the sky would be our first tantalizing clue that our web is not alone. Another method is to search for the fundamental grain of spacetime. If our universe is one of many, the very fabric of reality might have a pixelated structure at the tiniest scale, a remnant of its quantum origins in a greater multiversal landscape. The cosmic web we call home may be the ultimate expression of a cosmic accident, a single, beautiful pattern in an infinite tapestry of possibilities, leaving us to wonder if every possible structure, no matter how strange, is woven somewhere in the boundless dark. From the invisible grip of dark matter to the relentless push of dark energy, from the synchronized spin of galaxies to the profound emptiness of cosmic voids, these 50 mysteries are not isolated curiosities. They are interconnected threads in a single, magnificent tapestry, the cosmic web. This vast architecture is both our greatest map of the universe and our greatest puzzle, a structure that reveals the hidden laws of physics even as it conceals the true nature of reality. It is a story written in gravity, painted with light, and governed by forces we are only beginning to perceive. Every filament, every void, every anomalous alignment is a question waiting for an answer. So we turn this final question to you. As you look up at the night sky, which of these cosmic mysteries captures your imagination the most? Is it the ghostly presence of dark matter, the ultimate fate of the universe in the grip of dark energy, or the eerie synchrony of galaxies across billions of light years? Share your thoughts and never stop wondering about the hidden architecture of our incredible cosmos.